Hello and welcome back to Sleep Scientist. I'm so glad you've joined me tonight for another gentle journey through the cosmos. If you're settling into bed, curling up on your favorite chair, or simply trying to wind down after a long day of existing in this gravity-bound world, you found the perfect place to let your mind drift. Tonight, we're embarking on one of the most fascinating and frankly terrifying thought experiments in all of physics. We're going to explore what would happen if gravity, that invisible force that keeps your feet planted on the ground, your coffee in your cup, and our entire universe held together simply stopped working. Now, I should warn you up front, this might be either the most relaxing or the most unsettling video you've ever fallen asleep to. We're going to witness the gentle unraveling of reality itself, but we'll do it together, slowly and thoughtfully. Like watching a cosmic sunset that lasts for eternity. Before we float off into this strange new reality, I'd love it if you gave this video a gentle tap of appreciation and maybe subscribed if you haven't already. It really helps this sleepy little corner of science grow. And please, tell me in the comments, where are you listening from tonight, and what time is it in your part of the world? Are you drifting off in London at midnight, or perhaps it's a quiet afternoon in Sydney? I love seeing how our little community of curious minds spans the globe. Now, get comfortable. Adjust your pillows, pull up that blanket, maybe set your phone aside. You don't need to remember every detail of what we're about to explore. You don't need to take notes or solve equations. Just let your mind float along with the ideas, like an astronaut in a world where up and down have lost all meaning. This video is intended for educational and relaxation purposes only. It should not be considered as scientific advice or a substitute. For professional consultation, though I suppose if gravity actually stopped working, professional consultation would be the least of our worries. Are you ready? Let's begin this impossible journey together, starting with a simple question that will take us to the very edges of physical reality. Before we can imagine a world without gravity, we need to understand what we're losing. Gravity is perhaps the most familiar yet least understood force in our daily lives. Now, as you listen to this, gravity is pulling you toward the center of the earth with a force that's perfectly calibrated to your mass. It's holding the air in your lungs, the blood in your veins, and every atom in your body in its proper place. But what is gravity really? For most of human history, we thought of it as a pulling force, like an invisible hand reaching out from massive objects and tugging on everything around them. Sir Isaac Newton described it beautifully with his law of universal gravitation. Every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between. Then picture Newton sitting under his famous apple tree. When that apple fell in, yes, this probably did happen, though perhaps not quite as dramatically as the story suggests, he realized something profound. It's the same force pulling the apple toward Earth was holding the moon in its orbit. The same invisible influence keeping his feet on the ground was orchestrating the cosmic dance of planets around the sun. But then, along came Albert Einstein. With his wild hair and his tendency to revolutionize everything we thought we knew about reality, Einstein showed us that gravity isn't really a force at all, something far more elegant and strange. The curvature of space-time itself. Imagine you're lying on a trampoline. Place a bowling ball in the center, and the fabric dips and curves around it. Now roll a marble across the surface. Instead of traveling in a straight line, it curves around the depression created by the bowling ball. That's essentially how gravity works, according to Einstein. Massive objects like stars and planets create curves in the fabric of space-time, and smaller objects follow those curves. This isn't just a metaphor, it's literally how the universe operates. Space and time themselves bend and warp in the presence of mass and energy. What we experience as the force of gravity is actually us following the straightest possible path through curved space-time. When you're sitting in your chair right now, you're not being pulled down by some mysterious force. You're simply following the curvature of space-time created by Earth's mass. It's a bit like being in a car that's going around a curve. You feel pushed to one side, but really, you're just trying to continue in a straight line while the car follows a curved path. Gravity is the car, space-time is the road. and you're the passenger along for the ride. This understanding makes gravity both more beautiful and more terrifying when we imagine it disappearing. We're not just losing a force, we're losing the very structure of space-time itself. We're imagining a universe where the fabric of reality suddenly goes flat, where the cosmic trampoline loses all its curves and dips. But let's not get ahead of ourselves. Let's start small, with you, right where you are. In this moment when gravity still works perfectly, so here we are, about to embark on the strangest journey imaginable. In our thought experiment, gravity doesn't gradually weaken or slowly fade away. One moment it's there, holding everything together, as it has for 13.8 billion years. And the next moment, nothing. The fundamental force that shapes reality simply switches off, like someone flipping a cosmic light switch. But before we flip that switch, let's take a moment to appreciate what we're about to lose. Look around you right now. Everything you see exists in its current form because of gravity. The walls of your room aren't floating away because gravity holds the materials together. The air you're breathing forms a comfortable atmosphere around our planet because gravity keeps it from drifting off into space. Your body, marvel of biological engineering, relies on gravity in ways you probably never think about. Your blood circulates partly because your heart has learned to work with and against gravitational pull. Your inner ear uses tiny calcium carbonate crystals that respond to gravity to help you maintain balance. Even your bones and muscles have developed their strength in response to living in a gravitational field. The earth beneath you is round because gravity pulled all that rock and metal into the most efficient shape for mass distribution: a sphere. The continents, the oceans, the atmosphere, the delicate dance of weather patterns. All of it exists because gravity provides the stage on which these planetary processes can perform. Zoom out further, and gravity becomes even more essential. The moon orbits Earth because gravity provides the perfect balance between the moon's momentum and our planet's pull. Earth orbits the sun in that comfortable zone where liquid water can exist because gravity keeps us at just the right distance. The sun itself exists because gravity compressed a cloud of hydrogen and helium until it became hot and dense enough for nuclear fusion to begin. Our entire galaxy, the Milky Way, is a magnificent spiral of hundreds of billions of stars, all held together by gravity. The galaxy next door, Andromeda, is slowly approaching ESS. We're going to collide in about 4.5 billion years because gravity operates across these unimaginable distances. Even the largest structures in the universe, the cosmic web of galaxy, clusters separated by vast voids, exist because gravity has been patiently gathering matter together for billions of years, creating the beautiful, complex architecture of reality. Now, imagine all of that simply stops. There's no transition period, no warning signs, no gradual weakening. In our thought experiment, at some arbitrary moment, let's say right now, as you listen to these words, gravity vanishes completely from the universe. The curvature of space-time suddenly flattens out. Cosmic trampoline goes slack. What happens? First, let's start with the most immediate and personal experience. What happens to you in the first few seconds after gravity disappears? If you're lying down right now, you might not notice anything immediately. You're already supported by your bed or couch, and without gravity, you'd simply continue lying there. The pressure you feel from the mattress beneath you would gradually lessen as your body stops being pulled downward. But the change might be subtle at first, but if you're sitting up or standing, the experience would be immediate and disorienting. The moment gravity vanishes, you would stop being pulled toward the earth. But here's the thing. You wouldn't immediately float upward like a balloon. You'd simply become weightless, like an astronaut in the International Space Station. Think about this carefully. You're not suddenly repelled by the Earth. There's no upward force acting on you. You just stop being pulled down. If you were perfectly still when gravity disappeared, you'd simply hover in place, suspended in the air where you were standing. But of course, you're never perfectly still. The Earth is rotating at about 1,040 miles per hour at the equator. and you've been rotating with it your entire life. When gravity disappears, you'd continue moving in the direction you were already going. But now, there would be nothing to curve your path and keep you moving in a circle with the planet. Imagine you're on a merry-go-round, holding tightly to one of the horses. If you suddenly let go, you don't fly backward, you fly off in whatever direction the merry-go-round was carrying you at that moment. When gravity lets go of you, the same thing happens on a planetary scale. So depending on where you are on Earth and what time of day it is, you might find yourself drifting eastward at hundreds of miles per hour. But this movement would be gradual and smooth. You wouldn't feel it any more than you feel the Earth's rotation right now. What you would feel is a strange sensation of weightlessness. Your inner ear, which has spent your entire life detecting the pull of gravity, would suddenly receive no signal at all. You might feel dizzy, disoriented, perhaps nauseous. Astronauts call this space sickness, and it affects about half of all people who experience zero gravity for the first time. Your hair, if it's long enough, would slowly begin to float around your head in that characteristic astronaut style. Any loose clothing would billow gently around your body. If you had a drink in your hand, the liquid would form a perfect sphere and float away from the cup in a shimmering, wobbling ball. But let's talk about your room, because this is where things start to get really interesting. Everything that was resting on something else would begin to separate. Books on shelves would slowly drift away from the shelves. Picture frames would detach from walls, not because of any outward force, but because the tiny vibrations in the building, the microscopic movements that gravity usually dampens, would now be free to accumulate. Your furniture would begin a slow dance. Chairs and tables would gradually separate from the floor, not quickly or violently, but with a gentle, dreamlike quality. A pencil balanced on a desk would simply hang in the air, no longer knowing which way is down because there is no down. Any more dust particles, usually too heavy to float for long, would remain suspended in the air indefinitely. The air itself would start to behave differently. Without gravity to create pressure gradients, the atmosphere would begin to spread out more evenly. But we'll come back to that atmospheric crisis in a moment. If you tried to walk, you'd find it impossible in the traditional sense. Every step that would have normally pushed against the ground would instead push you away from the ground. You'd need to learn to move like an astronaut, pushing off surfaces and controlling your momentum carefully. The most psychologically difficult aspect might be the loss of a fundamental reference frame. For your entire life, you've known which way is up and which way is down. Every room has a floor and a ceiling. But now, these concepts would become meaningless. The floor is just another wall, and the ceiling is just another wall. And you're floating somewhere in the middle of a cubic space that no longer has any inherent orientation. It's a strange thing to contemplate, isn't it? It's the idea that concepts, as basic as up and down, are not fundamental properties of reality, but simply consequences of living in a gravitational field. Without gravity, there is no up or down, just 6 walls surrounding you in 3-dimensional space. But while you're adjusting to this new reality, much larger and more catastrophic changes would be beginning outside your window. Now let's step outside your floating room and consider what's happening to the air around you. This is where our thought experiment takes its first truly frightening turn. Earth's atmosphere, the air you breathe, all the oxygen that keeps you alive, all the nitrogen that makes up most of what we call Aries, held to our planet entirely by gravity. The atmosphere doesn't want to be here. The molecules of air are constantly moving, bouncing around at hundreds of miles per hour. And if given the chance, they would happily spread out into the infinite vacuum of space. The only reason we have an atmosphere at all is because Earth's gravity is strong enough to keep those air molecules from achieving escape velocity. It's like having a blanket that's constantly trying to float away, but gravity keeps pulling it back down around the planet. The moment gravity disappears, this delicate balance is shattered. Picture the atmosphere as a soap bubble surrounding the Earth. When gravity vanishes, it's as if someone pops that bubble. The air doesn't disappear instantly. That would actually be a mercy. Instead, it begins to expand outward into space at the speed of sound. Let's think about what this means. For you, still floating in your room, initially, you might not notice much difference. There's still air around you, still oxygen to breathe. But the pressure would begin to drop, slowly at first, then more rapidly. You know that feeling when you're in an airplane and your ears pop? During takeoff, that's your body adjusting to a decrease in air pressure. Now imagine that sensation continuing indefinitely, getting more and more intense as the minutes pass. The air pressure at sea level is about 14.7 pounds per square inch. That might not sound like much, but consider that this pressure is pushing on every square inch of your body. Right now, the air inside your lungs is at the same pressure as the air outside, so you don't feel this crushing force. But as the atmosphere expands into space, the external pressure would begin to drop rapidly. If you've ever seen a science demonstration where they pump the air out of a sealed container with a balloon inside, you know what happens next. But the balloon expands as the external pressure decreases. Your body would do the same thing. But here's where it gets particularly unpleasant to think about. Your body is essentially a pressurized vessel. Your blood, your other bodily fluids, they're all under pressure. As the external air pressure drops, the dissolved gases in your blood, particularly nitrogen, would begin to form bubbles. This is the same thing that happens to deep-sea divers who surface too quickly, a condition called decompression sickness or the bends. But in our scenario, it would be happening to everyone on Earth simultaneously, and far more rapidly than any diver has ever experienced. Within a few minutes, as the air pressure dropped to less than half of its normal value, you would begin to lose consciousness. Your blood wouldn't be able to carry oxygen efficiently. You might feel like you were suffocating, even though there was still air around. You too breathe. The saliva on your tongue would begin to boil, not because it's hot, but because at low pressures, water boils at much lower temperatures. The moisture in your mouth and on your skin would start to vaporize. This is not a pleasant image, I know. But remember, we're exploring this impossible scenario from the safety of a universe where gravity still works perfectly. You're still here, still breathing normally, still held gently, but firmly in gravity's embrace. As the atmosphere continued to expand, the air would become thinner and thinner. The sky, which appears blue because of the way our atmosphere scatters sunlight, would gradually fade to black. Without enough air molecules to scatter the light, the sky would look like it does from space, a field of brilliant stars against the deepest black, the weather. That complex dance of air masses and pressure systems that has shaped Earth's climate for billions of years would simply cease. No more wind, because wind is just air moving from high pressure to low pressure areas. No more clouds, because clouds depend on water vapor being held in the atmosphere by air pressure. No more storms. No more gentle breezes. No more of the atmospheric music that has provided the backdrop to every life that has ever existed on Earth. Within hours, most of the atmosphere would have expanded so far into space that Earth would be essentially airless. Like the moon, the planet would retain some atmosphere for a while. The heavier molecules would expand more slowly. But the oxygen you need to breathe would be among the first to go. But even as this atmospheric catastrophe unfolds, other changes would be happening to the water on our planet. Changes that would be visible from space as a completely unprecedented reorganization of Earth's surface. Water, like everything else on Earth, exists in its current distribution because of gravity. The oceans pool in the lowest areas of the planet's surface. Rivers flow downhill. Lakes form in depressions. Rain falls down from clouds. All of this happens because water, being denser than air, is pulled more strongly by Earth's gravitational field. Take away gravity, and water's behavior becomes completely alien. Let's start with the oceans, those vast bodies of water that cover about 71% of Earth's surface. Right now, the average depth of the ocean is about 2.3 miles, and the deepest point, the Challenger Deep in the Mariana Trench, goes down almost 7 miles. All of this water is held in these oceanic basins by gravity. Gravity disappears. The oceans don't suddenly leap into space. Instead, something far more mesmerizing and terrifying happens. They begin to float. Picture the largest raindrop you've ever seen. Then imagine it the size of a continent. Without gravity to pull water downward, and without solid boundaries to contain it, water naturally forms spheres. It's the shape that minimizes surface tension. So the oceans would begin to gather themselves into massive floating spheres of water. The Pacific Ocean, it's containing about 50% of all the water on Earth, would slowly coalesce into a sphere roughly 860 miles in diameter. That's a ball of water larger than the distance from New York to Chicago, just hanging in space where the Pacific used to be. The Atlantic would form its own sphere, maybe 700 miles across. The Indian Ocean, the Arctic Ocean, each would become its own floating water world, drifting away from the Earth's surface as the planet's rotation carries the solid ground away from where the water used to rest. But the process wouldn't be clean or quick. As these massive bodies of water reorganize themselves, they would create currents and movements unlike anything ever seen on Earth. Imagine tsunamis. But instead of water rushing across land, you'd have mountains of water flowing through the air, seeking to join with other water and form those perfect floating spheres. Coastal cities would face a phenomenon that no emergency plan has ever considered: the ocean simply leaving. Not receding slowly like an extreme low tide, but actually floating away as a coherent mass. Ships and harbors would find themselves suddenly sitting on what used to be the ocean floor, surrounded by floating spheres of seawater. Rivers would behave even more strangely. Right now, rivers flow because gravity pulls water downhill, seeking the lowest possible level, usually the sea. Without gravity, rivers would have no reason to flow at all. The water in rivers would simply hang in the air above the riverbeds like liquid snakes frozen in time. But here's where it gets really surreal. The water wouldn't stay in those river-shaped formations for long. Water has cohesive properties. Molecules are attracted to each other, so the river water would gradually pull itself together into spherical drops. The Mississippi River would become a chain of water spheres stretched across the American continent, each one slowly merging with its neighbors until the entire river system became one large floating lake. Waterfalls would be particularly spectacular in their transformation. Imagine Niagara Falls. Right now, water plunges 167 feet because gravity pulls it down. Without gravity, that water would simply hang in the air like a frozen curtain. But water's surface tension would gradually pull this curtain into drops, and those drops would merge into larger spheres, creating a floating water sculpture where the waterfall used to be. Lakes would face their own crisis. Most lakes exist in depressions in the landscape, natural bowls carved by glaciers, or formed by geological processes. When gravity disappears, there's nothing keeping the water in these bowls. Lake water would rise up out of its banks, not flowing over them, but literally floating up and away. The Great Lakes, containing about 20% of the world's fresh surface water, would become 5 enormous floating spheres. Lake Superior alone would form a water sphere about 200 miles in diameter, drifting somewhere above what used to be the border between the United States and Canada. Swimming pools would empty themselves in the most gentle way, would simply rise up and float away, forming perfect spheres in people's backyards. Hot tubs would become floating balls of warm water. Every bathtub, every sink full of water, every puddle on the street would lift off and join the strange new dance of floating water that was reorganizing itself across the planet. And then there's the water inside living things. Your body is about 60% water. Trees are up to 95% water. All of this biological water is currently held in place by cell walls, membranes, and yes, gravity. While the structural integrity of living cells might keep most biological water in place, initially, the absence of gravity would certainly affect how fluids move through organisms. Blood circulation, which relies partly on gravity to help return blood to the heart, would face new challenges. Plants, which use gravity to know which way to grow their roots and shoots, would lose this fundamental guidance system. But perhaps most beautiful and terrifying of all would be the rain that was already falling when gravity stopped. Every raindrop in the sky would suddenly hang suspended in midair, creating vast three-dimensional fields of floating water spheres. A rainstorm would become a floating sculpture, billions of water droplets arranged in the complex patterns they held at the moment gravity disappeared. It's a breathtaking image, isn't it? The Earth's water, which has flowed and pooled and fallen for billions of years, suddenly free to form whatever shapes the laws of physics allow, creating a planet decorated with floating oceans and flying rivers. But while the water finds its new equilibrium, the solid structures that civilization has built would be facing their own gravitational crisis. Now let's turn our attention to the human-built world. Cities and structures that represent thousands of years of architectural evolution, all designed with one fundamental assumption, that gravity will always pull everything downward. Every building you've ever been in, from the humblest house to the tallest skyscraper, exists in its current form because architects and engineers have spent centuries learning to work with gravity. We build foundations that go deep into the ground. We use materials that can bear weight. We design structures to channel the downward force of their own mass in the things contained into the solid earth below. Take away gravity, and every one of these design principles becomes not just unnecessary, but potentially dangerous. Let's start with skyscrapers, those monuments to human ambition that reach hundreds of stories into the sky. The Empire State Building, the Willis Tower, the Burj Khalifa, all of these structures exist because engineers found ways to build upward against gravity's pull. But skyscrapers aren't just tall. They're also incredibly heavy. The Empire State Building weighs about 365,000 tons. That's the mass of about 180,000 cars, all stacked up into a single structure. Right now, all of that weight is pressing down through the building's steel frame into its foundation, which distributes the load into the bedrock beneath Manhattan. When gravity disappears, that enormous mass doesn't disappear with it. The building still has the same amount of matter, the same inertia, the same tendency to keep doing whatever it was doing before. But now there's nothing pulling it downward, nothing keeping it anchored to its foundation. Here's where physics gets interesting. The building wouldn't immediately float upward like a balloon. It would simply become weightless, hanging in space where it stood. But buildings are constantly experiencing tiny forces, wind pushing against their sides, the thermal expansion and contraction of materials as temperatures change, even the microscopic vibrations from traffic and human activity. Normally, gravity overwhelms all of these tiny forces, keeping buildings firmly planted. But without gravity, these small forces would become significant. A strong wind could literally blow a skyscraper away from its foundation, causing it to drift across the city like a massive sailing ship. The connections between different parts of buildings would face new stresses. Right now, bolts and welds and concrete bonds are designed to handle the compressive forces of gravity pushing down. But in a weightless environment, these same structures might be subjected to tensile forces pulling apart rather than pressing together, for which they weren't designed. Windows, designed to be held in their frames by gravity and careful engineering, might begin to work loose, not catastrophically, but gradually, as the tiny forces that gravity usually dampens begin to accumulate. Imagine windows slowly drifting out of their frames and floating away like rectangular bubbles. Bridges present their own fascinating scenario. Most bridges are marvels of engineering that use gravity to their advantage. Suspension bridges like the Golden Gate Bridge use the weight of the roadway to create tension in the cables. Arch bridges use compression to channel weight through their curved structures. Beam bridges simply rest on their supports, held down by their own weight. Remove gravity, and bridges would face an identity crisis. The Golden Gate Bridge's roadway would no longer pull down on the suspension cables. The cables, no longer under tension, would go slack. The roadway itself, no longer held down by its own weight, could be lifted by the wind and float away from its supports like a ribbon. Stone arch bridges, some of which have stood for thousands of years, depend entirely on gravity to keep their stones pressed together. Without that downward force, the stones would simply drift apart, and these ancient structures would disassemble themselves peacefully, each stone floating in the space where it once helped support the bridge. Dams represent perhaps the most dramatic. An example of structures designed to work with gravity. Dams hold back water by using their own enormous weight to resist the pressure of the water behind them. The Hoover Dam, for example, weighs about 6.6 million tons. That immense mass, pressed firmly into the bedrock of the Colorado River Canyon, is what allows it to hold back Lake Mead. Without gravity, dams would lose their ability to resist water pressure. But this might not matter much, because as we discussed earlier, the water they're holding back would be floating away anyway. You'd have the surreal sight of massive concrete structures like the Hoover Dam hanging in the air above empty riverbeds, while the water they used to contain floated in spherical lakes somewhere overhead. Houses and smaller buildings would face their own challenges. Most houses are built with wooden frames that rely on gravity to keep joints tight and materials pressed together. Without gravity, some structures might literally shake apart over time as thermal expansion. Wind and other small forces gradually work loose the connections that gravity used to keep tight. Roofs, designed to shed rain and snow downward, would become meaningless. But this might not matter, since rain would no longer fall and snow would float rather than accumulate. Chimneys would face an existential crisis. The entire principle of how chimneys work, hot air rising because it's less dense than cold air, depends on gravity creating differences in pressure at different heights. Without gravity, there would be no up for hot air to rise toward. Fireplaces would become impossible to use safely. Smoke would have no reason to go up the chimney and out of the house. Elevators would become both unnecessary and impossible. Unnecessary because there would be no up or down to travel between. It's impossible because elevators work by using counterweights and gravity to efficiently move people between floors. In a weightless world, you could simply push off from any surface and float to wherever you needed to go within a building. Stairs. You wouldn't need to climb from floor to floor. You could simply float from one level to another. The entire concept of floors and levels would become somewhat meaningless anyway. Since there would be no gravitational down to define what constitutes a floor, perhaps most poignantly, all the infrastructure we've built to move things from place to place would become obsolete overnight. Roads, designed for vehicles that need friction with the ground to move, would be useless. Cars and trucks would float off the pavement. Highways would become empty ribbons of concrete stretching across the landscape, slowly accumulating floating vehicles like some surreal automotive art installation. Railways would face the same fate. Trains stay on tracks because gravity pulls them down onto the rails. Without gravity, trains would simply float off their tracks the moment they tried to move. The entire transportation network of civilization would become a museum of how we used to move things when there was still an up and down. Airports would be filled with aircraft that could no longer take off in any meaningful sense. Airplanes generate lift by creating lower pressure above their wings than below. But above and below would be meaningless concepts. Jets would become massive sculptures, their sophisticated aerodynamics useless, in a world where there's no preferential direction for air to flow. It's a humbling thought, isn't it? All of human civilization, every structure we've ever built, every system we've designed, all of it assumes that gravity will always be there. Pulling things toward the center of the earth, remove that assumption, and the physical framework of human society would need to be completely reimagined. But even as our cities float apart and our buildings become weightless sculptures, much larger changes would be happening to the planet itself. Now we come to one of the most profound consequences of losing gravity. Our planet itself would begin to fall apart. This might be the most difficult part of our thought experiment to truly comprehend, because we're so accustomed to thinking of Earth as solid, permanent, unchanging on human timescales. But the truth is, our planet is round because of gravity. It's not naturally spherical. It became spherical because over billions of years, gravity pulled all of Earth's matter toward the center, creating the most efficient possible shape for distributing mass in a gravitational field. Let me help you. Visualize this. Imagine you have an enormous pile of sand, rocks, and metal. If you pile it up in zero gravity, you could make it any shape you want: a cube, a pyramid, a sculpture of your favorite pet. But turn on gravity, and something beautiful happens. Every grain of sand, every pebble, every chunk of metal gets pulled toward the center of mass. The pile naturally arranges itself into the most stable possible configuration: sphere. That's exactly what happened when Earth formed 4.5 billion years ago. Our planet began as a disk of dust and debris orbiting the young sun. Gravity caused. This material too clumped together, and as the clumps grew larger, their gravitational pull became stronger, attracting more material. Eventually, so much matter accumulated that gravity compressed it all into a roughly spherical shape. But Earth isn't a perfect sphere. It's actually slightly flattened at the poles and bulges a bit at the equator, creating a shape called an oblate spheroid. This happens because the Earth rotates, and the centrifugal force from this rotation works against gravity, making the planet slightly wider than it is tall. Even this subtle shape is the result of a delicate balance between gravitational forces and rotational forces. Now, imagine gravity suddenly vanishes. The first thing to understand is that Earth wouldn't immediately fly apart like an explosion. The rocks and soil and metal that make up our planet would still have the same inertia they always had. They wouldn't suddenly gain energy and blast off in all directions. Instead, something more subtle but equally dramatic would begin to happen. Without gravity pulling everything toward the center, the internal structure of the Earth would start to change. Right now, the pressure deep inside our planet is enormous, millions of times greater than atmospheric pressure. Because of the weight of all the rock and metal pressing down from above, this pressure is what keeps the Earth's core solid and dense. What maintains the distinct layers of crust, mantle, and core that we learned about in school. Remove gravity, and this pressure would begin to decrease. Not instantly, but gradually, as the forces holding everything together weakened. The materials that make up the Earth's interior would begin to expand, like a compressed spring slowly returning to its natural length. The Earth's core, which exists as a solid ball of iron and nickel under tremendous pressure, would start to behave differently. At the center of the Earth, the pressure is about 360 gigapascals. That's 3.6 million times the pressure of Earth's atmosphere. This pressure is what keeps iron solid at temperatures of about 10,000 degrees Fahrenheit. Without the pressure created by gravity, the core might actually melt or expand, even though it's not getting any hotter. But the most visible changes would happen at the surface. The Earth's crust, that thin shell of rock that we live on, is held together partly by gravity and partly by the geological forces that formed it. Mountains exist because tectonic forces pushed rock upward, and gravity wasn't strong enough to pull them back down to sea level immediately. Without gravity, mountains would begin to lose their structural integrity. The rocks that make up a mountain range are held in place by friction, by interlocking crystal structures, and yes, by their own weight pressing down. Remove the weight, and mountains would slowly begin to crumble and disperse. But this wouldn't happen violently. Instead, you might see something hauntingly beautiful. Mountain ranges slowly dissolving into clouds of floating rock, each boulder and pebble drifting away from its neighbors like a three-dimensional sculpture, coming apart in slow motion. The Himalayas, the Rocky Mountains, the Andes, all of these magnificent geological features would gradually disassemble themselves, not through any destructive force, but simply because there would no longer be anything holding them. Together in their towering configurations, valleys and canyons, carved over millions of years by the downward flow of water under gravity's influence, would lose their meaning. The Grand Canyon is a mile-deep gouge in the Earth's surface because the Colorado River is pulled by gravity, carved downward through rock for millions of years. Without gravity, there would be no downward for rivers to carve toward. The very concept of sea level, the baseline measurement that we use to determine the height of everything on Earth, would become meaningless. Sea level exists because gravity pulls water into the lowest possible places on Earth's surface. Without gravity, there would be no lowest places, no natural baseline, no reference point for determining relative heights. Perhaps most strangely, the Earth's shape would gradually become less and less spherical, without gravity constantly pulling material toward the center. Our planet would slowly spread out, becoming less dense, less compact. The process would be incredibly slow by human standards. It might take thousands or millions of years, but eventually, Earth might resemble a loose cloud of debris rather than a solid planet. This spreading wouldn't happen uniformly. Different materials have different properties. Rock might hold together longer than soil. Metal might clump differently than stone. Over time, the Earth might separate into different floating clouds of material, each one composed of similar substances, creating a solar system littered with the dispersed remains of what used to be a planet. The implications for life are staggering. All life on Earth evolved in a gravitational field. Plants grow toward light and against gravity. Animals develop skeletal and muscular systems designed to work with and against gravitational pull. The very concept of orientation, knowing which way is up, is fundamental to how life processes work. Even if the atmosphere weren't escaping into space, even if the oceans weren't floating away, life would face unprecedented challenges in a world where up and down no longer existed, where the ground itself was slowly dispersing into space. But while the Earth gradually loses its shape, our closest celestial neighbor would be facing its own crisis of orbital mechanics. The Moon is a faithful companion that has hung in Earth's sky for over 4 billion years, exists in its orbit entirely because of gravity. It's a delicate dance. The Moon's momentum carries it forward, trying to fly off into space in a straight line, while Earth's gravity constantly pulls it inward, curving its path into an orbit. This gravitational relationship between Earth and Moon is so fundamental that it affects everything from ocean tides to the length of our days. The Moon's gravitational pull creates the tides by pulling more strongly on the water that's closer to it than on the water that's farther away. This same tidal force gradually slows Earth's rotation, making our days longer by about 2.3 milliseconds per century. When gravity disappears, this ancient partnership ends immediately. The Moon, at the moment gravity stops working, is traveling around Earth at about 2,288 miles per hour. That's its orbital velocity, the speed it needs to maintain to stay in orbit. But orbital motion only makes sense in the presence of a gravitational field. Without gravity to curve its path, the Moon would simply continue moving in whatever direction it was heading at the moment gravity disappeared. Let's think about what this means. If gravity vanished when the Moon was at the point in its orbit where it's moving most directly away from Earth, our satellite would continue flying away in a straight line at over 2,000 miles per hour. Within just 24 hours, it would be more than 55,000 miles farther from Earth than it is now. Within a week, it would be farther away than it has been since the solar system formed. But the Moon's departure wouldn't be clean or simple, because it's not just Earth's gravity that affects it. The Moon also experiences gravitational pull from the Sun, which is much more massive than Earth, but also much farther away. Right now, this solar gravitational pull is incorporated into the Moon's complex orbit around Earth, without Earth's gravity to anchor it. The Moon would essentially become a small planet orbiting the Sun directly, depending on where it was in its orbit around Earth when gravity stopped, and what time of year it was in Earth's orbit around the Sun. The Moon might end up in a stable solar orbit, or it might follow a chaotic path that could eventually lead it too crash into another planet or be ejected from the solar system entirely. The loss of the Moon would have profound effects on Earth, even beyond the obvious absence of that familiar face in the night sky. The Moon's gravitational pull, as we mentioned, creates our tides. Ocean tides rise and fall twice a day, because the moon's gravity pulls more strongly on the water that's closer to it. But it's not just ocean tides. The moon's gravity also creates atmospheric tides, subtle changes in air pressure as the moon passes overhead, and even solid earth tides, where the planet's surface rises and falls by several inches as the moon's gravity tugs on it. All of these tidal effects help stabilize Earth's rotation and climate. The moon acts like a gravitational gyroscope, keeping Earth's rotational axis from wobbling too dramatically. Without the moon's steadying influence, Earth's axis might wobble much more chaotically over geological time, leading to dramatic climate changes as different parts of the planet receive varying amounts of sunlight. But of course, in our thought experiment, these long-term climate effects would be the least of our worries. Since the atmosphere would already be escaping into space and the oceans would be floating away, the moon's departure would also own one of the most beautiful phenomena visible from Earth: solar eclipses. Solar eclipses happen because the moon is just the right size and distance from Earth to exactly cover the sun's bright disk when it passes between Earth and sun. This is an extraordinary cosmic coincidence. The moon is about 400 times smaller than the sun, but it's also about 400 times closer, making them appear almost exactly the same size in our sky as the moon drifted away into its new solar orbit. This perfect size match would be lost forever. There would be no more total solar eclipses, no more moments when day suddenly turns to night as the moon's shadow sweeps across the Earth. The phases of the moon, which have provided a natural calendar for human civilization since the beginning of recorded history, would also disappear. No more new moons, full moons, crescents, or gibbous phases. The word month, which comes from moon, would lose its astronomical meaning, but perhaps most poignantly, we would lose that sense of companionship that the moon has provided. For all of human history, people have looked up and seen the moon as a familiar presence, sometimes bright and full, sometimes a thin crescent, but always there, always moving through its reliable cycle. Poets have written about the moon. Lovers have gazed at it together. Werewolves have supposedly transformed by it. The moon has been humanity's constant companion, the one celestial object close enough to show a face, to have visible features, to feel like a place rather than just a point of light. In our gravity-free world, we would look up and see only stars, scattered points of light against the black of space. With no familiar nearby companion to anchor our sense of place in the cosmos, but the moon's departure would be just the beginning of the orbital chaos that would unfold throughout the solar system. Before we zoom out to look at the larger solar system, let's spend a moment considering what would happen to the geological processes that shape our planet. Earth is not a static ball of rock, it's a dynamic, active world where vast plates of crust constantly move, collide, and reshape the surface in a process we call plate tectonics. The entire theory of plate tectonics, which explains how continents drift, mountains form, and earthquakes occur, depends fundamentally on gravity. The movement of tectonic plates is driven by convection currents in the Earth's mantle, the layer of hot, semi-solid rock beneath the crust. These convection currents exist because hot rock, being less dense, tends to rise upward through cooler, denser rock, but only in the presence of gravity. Think of a pot of soup heating on a stove. The soup at the bottom gets hot and rises because it becomes less dense than the cooler soup above it. The cooler soup sinks to replace it, creating a circulation pattern. This only works because gravity provides a down for the dense material to sink toward and an up for the less dense material to rise toward. The same process happens in Earth's mantle, but incredibly slowly. Hot rock deep in the mantle rises over millions of years, carrying tectonic plates along like passengers on a very slow conveyor belt. When this hot rock reaches the upper mantle, it cools and sinks back down, completing the convection cycle. Remove gravity, and these convection currents would stop immediately. There would be no force to make dense, cool rock sink or light, hot rock rise. The mantle would still be hot. That heat comes from radioactive decay in Earth's core and wouldn't change. but the heat would have no way to organize itself into the circulation patterns that drive plate tectonics. This means that all the geological processes we associate with an active planet would gradually cease. No more earthquakes caused by plates grinding against each other. No more volcanic eruptions driven by magma rising through the crust. No more formation of new ocean floor at mid-ocean ridges. No more mountain building as plates collide and buckle. The ring of fire around the Pacific Ocean, that arc of volcanoes, and earthquake zones that marks the boundaries of tectonic plates would become geologically quiet. The San Andreas Fault, the boundary between the Pacific and North American plates that threatens California with major earthquakes, would stop accumulating stress. But this geological quieting wouldn't happen instantly. The Earth's crust would still retain all the stress and strain that is built up over millions of years of plate movement. This stored energy might be released in unusual ways as the planet's structure adjusts to the absence of gravity. Some areas of the crust that are currently under compression might expand as the weight pressing down on them decreases. Other areas that are under tension might release that tension in ways that could reshape the surface. The process would be unpredictable and unlike anything geologists have ever studied. Volcanic activity would face its own crisis. Right now, magma rises through the Earth's crust because it's less dense than the surrounding rock, and gravity pulls the denser rock down while allowing the lighter magma to float upward. Without gravity, there would be no force to drive magma upward through volcanic conduits. Existing volcanoes might stop erupting, but not because they're running out of magma. The magma would still be there, still hot, but it would have no reason to move in any particular direction. Volcanic mountains, built up over thousands of years by repeated eruptions, might slowly lose their shape as their structure no longer, held together by gravitational compression, gradually spreads out. The mid-ocean ridges, those underwater mountain chains where new ocean floor is constantly being created, would stop their geological activity. These ridges exist because magma rises from the mantle and solidifies into new rock, slowly pushing the ocean floor apart and creating new seafloor. Without gravity to drive the magma upward, this process of seafloor spreading would halt. Hot springs and geysers, those surface expressions of geothermal activity, would also change dramatically. Right now, underground water gets heated by contact with hot rock and rises to the surface because hot water is less dense than cold water. Geysers work because water heated deep underground becomes steam, expands, and forces its way upward through underground channels. In a gravity-free world, there would be no upward for hot water to move toward. Hot springs would stop flowing, and geysers would stop erupting. The entire hydrothermal system that brings Earth's internal heat to the surface would shut down. This might seem like a minor detail compared to the atmosphere escaping and the oceans floating away, but it represents the end of one of the most fundamental processes that has shaped our planet for billions of years. Plate tectonics isn't just responsible for earthquakes and volcanoes, it's also responsible for the formation of continents, the creation of mountain ranges, and even the regulation of Earth's climate through the carbon cycle. Over geological time, plate tectonics helps regulate Earth's temperature by moving carbon between the atmosphere, oceans, and rocks. When this system shuts down, it's not just the end of geological activity, it's the end of one of the planet's most important self-regulation mechanisms. But while Earth's internal processes wind down, the larger dance of celestial mechanics throughout the solar system would be collapsing in spectacular fashion. Now let's expand our view beyond Earth and consider what happens to the entire solar system when gravity, the force that has orchestrated the cosmic dance of planets for 4.6 billion years, simply vanishes. Every planet in our solar system exists in its current orbit because of a delicate balance between two forces: the planet's momentum, which wants to carry it off into space in a straight line, and the sun's gravitational pull, which constantly tugs it inward. This creates the elliptical orbits that keep planets at relatively stable distances from the sun. It's neither flying off into interstellar space nor spiraling into our star. When gravity disappears, this ancient choreography ends immediately. Start with Mercury, the innermost planet. whizzing around the sun at about 105,000 miles per hour. At the moment gravity stops working, Mercury is traveling faster than any other planet because it needs that speed to maintain its tight orbit so close to the sun. Without the sun's gravity to curve its path, Mercury would continue in whatever the direction it was heading at that moment, flying off into space at over 100,000 miles per hour. Venus, our nearest planetary neighbor, orbits the sun at about 78,000 miles per hour. Like Mercury, it would continue in a straight line from whatever point it occupied when gravity failed. Depending on where Venus was in its orbit at that moment, it might head toward the outer solar system, or it might actually angle back toward the inner solar system, creating the possibility of planetary collisions that were never possible when orbits kept planets in their designated lanes. Earth, as we've discussed, would continue at its orbital speed of about 67,000 miles per hour. But Earth's trajectory would be complicated by the fact that our planet wouldn't be a single, coherent object anymore. As we explored earlier, Earth itself would be slowly coming apart, dispersing into a cloud of debris. So what would actually be flying through space wouldn't be a planet, but rather a slowly expanding collection of rocks, soil, water spheres, and atmospheric gases, all traveling in roughly the same direction, but gradually spreading out. Mars, the red planet, would depart at about 54,000 miles per hour. This is particularly poignant when you consider that Mars is currently the focus of so much human attention as a potential second home for our species. All of our plans to colonize Mars, all of our robotic missions exploring its surface, all of our dreams of becoming a multiplanetary species assume that Mars will continue to exist in a stable orbit around the sun. In our thought experiment, Mars becomes just another X-planet flying off into the void. The outer planets present even more dramatic scenarios because they're so much more massive. Jupiter, the giant of our solar system, contains more mass than all the other planets combined. It's often called the vacuum cleaner of the solar system because its enormous gravitational pull has swept up countless asteroids and comets over the eons, protecting the inner planets from impacts. Jupiter orbits the sun at about 29,000 miles per hour. That might sound slow compared to the inner planets, but Jupiter weighs 318 times as much as Earth. When something that massive starts moving in a straight line at 29,000 miles per hour, it becomes an unimaginable force of destruction for anything. In its path, Saturn, with its magnificent rings, would depart at about 21,000 miles per hour. But Saturn's rings present their own fascinating substory. Those rings exist because countless chunks of ice and rock orbit Saturn, held in place by the planet's gravity. When gravity disappears, Saturn's rings would disperse like a cosmic flower blooming in slow motion, each particle of ice and rock continuing in whatever direction it was moving when the gravitational bonds were severed. Uranus and Neptune, the ice giants of the outer solar system, would also begin their own straight-line journeys into interstellar space, but their departure would be slower and more gradual, giving them a kind of dignity as they majestically drift away from the sun that has warmed them barely for billions of years. But here's where the story gets really interesting. Without gravity, there's no guarantee that planets would travel alone. Some planets might end up following similar trajectories, creating the possibility of slow-motion planetary collisions in deep space. Imagine Venus and Mars no longer bound to their separate orbital lanes, slowly converging over thousands of years until they collide in a spectacular but gentle meeting of worlds. The asteroid belt, that collection of rocky debris between Mars and Jupiter, would become a dispersing cloud of individual asteroids, each one flying off on its own trajectory. Some might follow paths that intersect with the trajectories of the departing planets, creating possibilities for impacts that could never have occurred when everything was locked in stable orbits. The outer reaches of the solar system would see their own form of chaos. The Kuiper Belt, that region beyond Neptune where Pluto and thousands of other small icy bodies orbit, would become a rapidly expanding shell of debris. Each object would continue at whatever speed it was traveling when gravity stopped, creating a complex three-dimensional dispersal pattern. The Oort cloud, spherical shell of comets that surrounds our entire solar system at distances up to 100,000 times farther from the sun than Earth is, would begin its own slow-motion explosion. These comets, barely held in solar orbit by the sun's weak gravitational influence at such enormous distances, would be among the first objects to escape completely into interstellar space. Perhaps most remarkably, the planet's moons would face their own individual crises. Each moon orbits its planet for the same reason planets orbit the sun: balance between momentum and gravitational attraction. When gravity disappears, every moon in the solar system would fly away from its planet. Jupiter has 79 known moons. Saturn has 82. Uranus has 27. Neptune has 14. All of these moons would suddenly become independent objects, each continuing in whatever direction it was traveling when gravity stopped. The night skies of these planets, if anyone were there to observe them, would gradually empty as their moons departed one by one. Earth's moon, as we discussed, would fly away at over 2,000 miles per hour. But consider Europa, one of Jupiter's moons, which might harbor life in its subsurface ocean. Europa would fly away from Jupiter, carrying its hidden ocean with it into the cold depths of space, ending any possibility that life might exist in that alien sea. The Galilean moons of Jupiter, Io, Europa, Ganymede, Callisto, have been Jupiter's companions for billions of years. Io, with its sulfur volcanoes powered by tidal heating from Jupiter's gravity, would see its volcanic activity stop as it departed from the gravitational forces that have kept its interior molten. Europa's ocean, kept liquid by the same tidal heating, would begin to freeze as its moon travels away from its parent planet. It's a cosmos-scale tragedy, isn't it? The breakup of gravitational families that have existed since the solar system formed. Jupiter, the king of planets, would find itself suddenly alone. No longer the center of its own miniature solar system of moons, but while the planets and moons scatter into space, the sun itself would be facing its own existential crisis. The sun, that ball of plasma that has provided light and warmth to our solar system for 4.6 billion years, exists entirely because of gravity. Everything about our star, its spherical shape, its internal structure, the nuclear fusion that powers it, even its ability to hold on to its own material, depends on gravitational forces. To understand what would happen to the sun without gravity, we need to think about what the sun actually is. It's not solid like a planet. It's not a ball of fire, despite appearances. The sun is a massive sphere of plasma-ionized gas, so hot that electrons have been stripped away from their atomic nuclei, held together entirely by its own gravitational pull. The sun contains about 99.86% of all the mass in our solar system. That's roughly 330,000 times the mass of Earth, all compressed into a sphere about 864,000 miles in diameter. This enormous mass creates gravitational forces strong enough to compress the sun's core to temperatures of about 27 million degrees Fahrenheit and pressures 250 billion times greater than Earth's atmospheric pressure. These extreme conditions are what make nuclear fusion possible. In the sun's core, hydrogen nuclei are moving so fast and are squeezed so tightly together that they overcome their natural electrical repulsion and fuse into helium, releasing tremendous amounts of energy in the process. This energy works its way outward through the sun's layers, eventually reaching the surface and radiating into space as the light and heat that make life on Earth possible. But nuclear fusion only happens under these extreme conditions of temperature and pressure. And those conditions only exist because gravity compresses the sun's material so intensely. Remove gravity, and the entire fusion process would shut down. Almost immediately, here's what would happen. The moment gravity disappears, there would no longer be any force holding the sun's plasma together. The sun's material, no longer compressed by its own weight, would begin to expand outward in all directions. But this expansion wouldn't be slow and gentle. Like the dispersal of Earth's atmosphere, the sun's plasma is incredibly hot and energetic. Without gravity to contain it, this material would expand explosively, like the ultimate fireworks show. The sun would essentially blow itself apart, not through any external force, but simply because its own internal energy would no longer be contained by gravitational compression. This expansion would happen at incredible speeds. The outer layers of the sun, no longer held down by the weight of the layers above them, would accelerate outward at hundreds or thousands of miles per second. The solar wind, that stream of charged particles that the sun constantly emits, would become a solar hurricane as vast amounts of plasma rushed outward into space. The sun's magnetic field is generated by the movement of electrically charged plasma within the sun. It's become chaotic and unpredictable as the plasma that creates it dispersed into space. Solar flares and coronal mass ejections. Those dramatic explosions of solar material that can affect electronics on Earth would become meaningless concepts because there would no longer be a coherent solar structure to produce them. But here's the most remarkable part. Even as the sun disperses, nuclear fusion in its core wouldn't just stop, would become impossible. The hydrogen nuclei in the expanding plasma would quickly spread out too far from each other to fuse. The temperature would drop as the plasma expanded and cooled. Within minutes, the nuclear furnace that has burned for billions of years would go cold. The light we see from the sun takes about 8 minutes and 20 seconds to reach Earth. So, for a brief period after the sun began dispersing, we would still see it shining normally in the sky, not yet knowing that our star was in the process of coming apart. Then, gradually, the sun would begin to dim and change color as its surface temperature dropped and its plasma dispersed. The sun wouldn't disappear instantly. Instead, it would transform from a bright, compact star into an enormous, dim, expanding cloud of hot gas. This cloud would continue to emit some light and heat, but much less than the concentrated fusion furnace we're used to. Over time, this expanding solar cloud would cool and dim until it became invisible, dispersed so widely through space that it would no longer function as a coherent energy source. The effects on the solar system would be immediate and catastrophic. All the planets, even if they were still in orbit, which they wouldn't be, since gravity would be gone, would quickly freeze as the sun's energy output plummeted. But of course the planets would already be flying away into space, so this cooling would be academic. More subtly, the loss of the sun's gravity would also affect the structure of space itself in our region of the galaxy. The sun creates a significant gravitational depression in the fabric of space-time that affects the motion of everything in the solar system. Without this gravitational influence, the region of space where our solar system used to exist would become gravitationally flat. It's no longer providing the organizing influence that has shaped the orbits of planets, asteroids, and comets for billions of years. The heliosphere, that bubble of solar wind that surrounds our entire solar system and protects us from some forms of cosmic radiation, would collapse as the sun's dispersing plasma weakened and spread out. This would leave the departing planets in debris. It's more exposed to cosmic rays and interstellar radiation. Perhaps most poignantly, the disappearance of the sun would mark the end of the astronomical unit, that fundamental measure of distance-based. On Earth's average distance from the sun, the O has been our cosmic ruler, the way we measure distances within the solar system. With no sun and no Earth orbit, this unit of measurement would become meaningless. Like trying to measure distance with a ruler that no longer exists. It's sobering to realize how completely our existence depends on the sun's gravity, not just for warmth and light, but for the very structure that makes the sun possible in the first place. Remove gravity, and our star doesn't just stop shining, it ceases to exist as a coherent object, dispersing into the cosmic background like a campfire whose logs have been scattered by an invisible wind. Between Mars and Jupiter lies one of the most fascinating regions of our solar system, the asteroid belt, a collection of rocky and metallic objects that represents the leftover building materials from the solar system's formation. This belt contains hundreds of thousands of asteroids, ranging from tiny pebbles to Ceres, a dwarf planet about 590 miles in diameter. The asteroid belt exists in its current form because of a delicate gravitational balance. The asteroids are held in their region of space by the competing gravitational influences of Mars pulling them inward, and Jupiter pulling them outward. This gravitational equilibrium has kept the belt stable for billions of years, preventing the asteroids from either falling into the sun or being ejected from the solar system. When gravity disappears, his ancient balance is shattered instantly. Each asteroid in the belt is traveling at its own orbital speed, typically between 40,000 and 60,000 miles per hour. The moment gravity stops working, every single asteroid would continue moving in whatever direction it was heading. But now in perfectly straight lines instead of curved orbits, the result would be one of the most spectacular dispersals in the solar system. Imagine hundreds of thousands of rocky objects, some as small as houses, others as large as mountains, all suddenly free from their gravitational constraints and spreading out into space, like the ultimate three-dimensional fireworks display. But this dispersal wouldn't be random. The asteroids' final trajectories would depend on exactly where they were in their orbits when gravity failed. Some asteroids, those that happened to be moving toward the inner solar system at that moment, would continue inward, potentially crossing the paths of the departing inner planets. Others, moving toward the outer solar system, would head outward into the realm where the gas giants used to orbit. This creates fascinating possibilities for encounters that could never have happened. When everything was locked in stable orbits, an asteroid that had spent billions of years safely orbiting between Mars and Jupiter might suddenly find itself on a collision course with Venus or Earth's debris cloud, leading to impacts that would be impossible under normal gravitational conditions. Ceres, the largest object in the asteroid belt and officially classified as a dwarf planet, would become an independent wanderer. At about 590 miles in diameter, Ceres is large enough to have a roughly spherical shape and may harbor water ice beneath its surface. In our thought experiment, Ceres would fly away from the asteroid belt at tens of thousands of miles per hour, carrying its potential water reserves into the depths of space. Some of the asteroids have highly elliptical orbits that bring them close to Earth during their normal journeys around the Sun. These near-Earth asteroids, which astronomers carefully track because of their potential impact hazard, would suddenly become much more unpredictable. An asteroid that was safely following a known orbit might suddenly veer off in a completely different direction, making it impossible to predict where it might go. The Trojan asteroids, as objects that share Jupiter's orbit but stay about 60 degrees ahead of or behind the giant planet, would face their own dispersal. These asteroids exist in gravitational balance points called Lagrange points, where the gravitational forces of the Sun and Jupiter create stable regions where small objects can remain. Without gravity, these Lagrange points would disappear, and the Trojan asteroids would scatter like marbles released from a bowl. But perhaps the most significant consequence of the asteroid belt's dispersal would be the loss of what astronomers call the grand tack effect. Jupiter's gravitational influence has historically acted like a cosmic shepherd, preventing asteroids from migrating inward toward the inner solar system where they might impact planets like Earth. Jupiter's gravity is essentially cleaned up the solar system, either capturing asteroids as its own moons or ejecting them entirely. With Jupiter flying away and its gravitational influence gone, its protective effect would disappear. While the timing wouldn't matter much in our thought experiment, since Earth would already be dispersing and uninhabitable, it's worth noting that one of the factors that has made Earth a safe place for life to evolve would no longer exist. Asteroid belt also contains the remnants of what might have been another planet. Some theories suggest that the material in the asteroid belt represents a planet that never quite formed. It's prevented from coalescing by Jupiter's gravitational interference. If gravity suddenly returned to the universe, these scattered asteroids would no longer have the opportunity to gravitationally attract each other and potentially form a planet, since they would be dispersed across vast regions of space. The metal-rich asteroids, those objects that contain valuable materials like platinum, gold, and rare earth elements, would also scatter across space. These asteroids represent potential mining targets for future space industries, containing more precious metals than exist in Earth's entire crust. In our gravity-free scenario, these treasure troves would become cosmic nomads. Wandering through interstellar space with their valuable cargo, some asteroids rotate rapidly, spinning like cosmic tops as they orbit the Sun. Without gravity, too, provide the centripetal force that keeps their material together. Some of these fast-spinning asteroids might actually fly apart due to centrifugal force, breaking into smaller fragments that would then scatter independently. The asteroid belt has also been a source of meteorites that have fallen to Earth. It's providing scientists with samples of primitive solar system material. Some of our most important insights into the formation of the solar system have come from studying these meteorites. In a universe without gravity, there would be no more meteorite falls, no more opportunities for space rocks to be captured by planetary gravity and delivered to the surface for study. It's remarkable to consider that the asteroid belt, which might seem like empty space scattered with a few rocks, actually represents a complex gravitational ecosystem that has remained stable for billions of years. The loss of gravity wouldn't just scatter the asteroids, it would end one of the longest-running examples of gravitational balance in our solar system. A celestial dance that has been performing the same routine since shortly after the planets formed, as we watch this ancient belt disperse into space. We're witnessing the end of one of the solar system's most persistent features. A reminder that even seemingly empty regions of space are actually intricate gravitational sculptures, shaped and maintained by invisible forces that we usually take for granted. Now let's expand our perspective to the largest scales imaginable, and consider what happens when gravity vanishes, not just from our solar system, but from our entire galaxy. This is where our thought experiment reaches truly cosmic proportions. Dealing with structures so vast that light takes hundreds of thousands of years to cross them. The Milky Way galaxy, cosmic home, is a barred spiral galaxy containing between 100 and 400 billion stars, along with countless planets, asteroids, comets, and clouds of gas and dust. The entire galaxy is about 100,000 light-years across and perhaps 1,000 light-years thick, making it roughly disc-shaped when viewed from the side. But here's the crucial point. This entire magnificent structure exists only because of gravity. Every star in the galaxy is held in orbit around the galactic center by gravitational forces. The spiral arms that give our galaxy its distinctive shape are maintained by gravitational interactions between stars and gas clouds. Even the supermassive black hole at the center of our galaxy, which weighs about 4 million times as much as our Sun, exists as a cohesive object only because its gravity is so strong that not even light can escape. When gravity disappears, the Milky Way doesn't just change, it ceases to exist as a galaxy at all. Let's start with the individual stars. Right now, every star in our galaxy is orbiting the galactic center at speeds ranging from about 140 miles per second for stars like our Sun and the outer regions to over 3,000 miles per second. 4 stars very close to the central black hole. These orbital speeds are necessary to balance the gravitational pull from all the mass in the galaxy's center. The moment gravity vanishes, every single star would continue moving in whatever direction it was heading, but now in straight lines. Instead of curved orbits, stars near the galactic center, moving at thousands of miles per second, would fly outward at incredible speeds. Stars in the outer regions, moving more slowly, would disperse more gradually, but just as inevitably. The result would be the most spectacular dissolution in the universe. 400 billion stars, each one potentially surrounded by its own system of planets, which would also be dispersing, as we've already discussed. It's all flying away from each other in different directions, gradually spreading out across ever larger volumes of space. The spiral arms of the Milky Way, those graceful curves of stars and gas that create the galaxy's iconic appearance, would lose all meaning. Spiral structure in galaxies is maintained by what astronomers call density waves, regions where gravitational forces cause stars and gas to bunch up temporarily as they orbit. Without gravity, these density waves would disappear instantly, and the spiral pattern would dissolve like smoke in a breeze. But the dispersal wouldn't be uniform. Different parts of the galaxy would scatter at different rates depending on how fast they were moving when gravity disappeared. The galactic bulge, that dense central region containing older stars, would explode outward rapidly because those stars were moving at high speeds in tight orbits. The outer regions, including our own local area around the Sun, would disperse more slowly. The supermassive black hole at the galaxy's center, known as Sagittarius A*, presents a particularly fascinating case. Right now, this black hole is defined by having so much mass compressed into such a small space that its gravitational pull prevents even light from escaping once it crosses the event horizon. But what is a black hole without gravity? It's a philosophical question that pushes at the boundaries of physics. The mass that makes up the black hole would still exist. Energy and matter don't just disappear when gravity stops working. But without gravitational forces to hold that mass together in its incredibly dense configuration, the black hole would, well, it would stop being a black hole. The mass that was previously compressed beyond the event horizon would suddenly be free to expand. It would likely explode outward in the most spectacular explosion imaginable, releasing all the energy that had been trapped within the black hole's gravitational prison. This explosion would dwarf anything we've ever observed in the universe, possibly outshining the rest of the dispersing galaxy combined. The gas and dust clouds that fill the space between stars would also begin to disperse. These interstellar clouds are the raw material for future. It's star formations where gravity slowly compresses gas and dust until it becomes dense and hot enough to ignite nuclear fusion and birth new stars. No mechanism for this compression, no way for new stars to form. This means that not only would existing stars fly away from each other, but the universe would lose its ability to create new stars entirely. The era of star formation, which has been ongoing for over 13 billion years, would end immediately and permanently. The globular clusters, those dense balls of ancient stars that orbit our galaxy like stellar satellites, would also disperse. These clusters, some containing hundreds of thousands of stars, packed into regions only a few light years across, exist only because their combined gravity holds them together. Without that gravitational glue, each globular cluster would scatter its stars across space like a cosmic dandelion, seedhead blown by an invisible wind. Our local stellar neighborhood would face its own dispersal. The stars nearest to our Sun, Proxima Centauri, Alpha Centauri, A and B, Barnard's Star, Wolf 359, and others, are all following their own independent orbits around the galaxy. When gravity stops, they would all continue in straight lines gradually, growing farther and farther apart. The local group, that collection of galaxies that includes the Milky Way, the Andromeda Galaxy, and several smaller galaxies, would also scatter. Right now, these galaxies are gravitationally bound to each other, slowly orbiting their common center of mass. Andromeda is actually approaching the Milky Way and is expected to collide with us in about 4.5 billion years. Without gravity, this cosmic collision would never happen instead. Andromeda would continue in whatever direction it was moving when gravity failed. The larger cosmic structures would disperse as well. Galaxy clusters, those groups of hundreds or thousands of galaxies, held together by gravity, would scatter their member galaxies across ever larger volumes of space. The cosmic web, that vast network of galaxy clusters connected by filaments of dark matter and gas, would dissolve as its structural framework disappeared. Even dark matter, that mysterious substance that makes up about 85% of all matter in the universe, would lose its ability to form the large-scale structures that shape the cosmos. Dark matter interacts primarily through gravity, so without gravitational forces, it would simply spread out uniformly through space. It's no longer able to create the invisible scaffolding that holds galaxies and galaxy clusters together. Of galactic neighborhoods, stellar systems, and cosmic addresses would become meaningless. Right now, we can describe our location in the universe with increasing levels of detail: Earth, solar system, local interstellar cloud, local bubble, Gould Belt, Orion Arm, Milky Way Galaxy, local group, Virgo supercluster, Laniakea supercluster. In a universe without gravity, none of these organizational structures would exist. Instead of living in a universe filled with galaxies, those beautiful spiral and elliptical collections of billions of stars, we would inhabit a cosmos where individual stars were scattered randomly through space, with vast empty regions between them growing larger and larger as time passed. The night sky, if there were still observers to see it, would gradually grow dimmer as nearby stars moved farther away. Their light redshifted and weakened by increasing distance. It's a profoundly lonely vision of the cosmos. A universe where every star is an island, drifting alone through the vast darkness, carrying its dispersing planetary system, if any, as it journeys through space with no destination and no companions. Just the memory of a time when galaxies existed and gravity held the universe together in beautiful, complex structures. As our view encompasses the fate of individual stars in a gravity-free universe, we encounter one of the most fundamental consequences of losing this essential force. Stars would not only drift apart from each other, but they would also lose their ability to exist as stars at all. To understand why, we need to think about what a star actually is. A star is essentially a perfect balance between two opposing forces: the inward pull of gravity trying to collapse the star's mass into a single point, and the outward pressure from nuclear fusion in the star's core pushing against that collapse. This balance is so precise that it can maintain itself for billions of years. Our sun, for example, has been burning steadily for about 4.6 billion years and has enough fuel to continue for another 5 billion years. All because the rate of nuclear fusion in its core produces exactly the right amount of outward pressure. To balance the inward pull of its own gravity, remove gravity from this equation, and stars would face an immediate crisis. Let's start with our sun again, since it's the star we know best. As we discussed earlier, the sun's core reaches temperatures of about 27 million degrees Fahrenheit and pressures 250 billion times greater than Earth's atmosphere. These extreme conditions exist only because the sun's own gravity compresses its material so intensely that hydrogen nuclei are forced together. Despite their natural electrical repulsion, the moment gravity disappears, this compression would end. The sun's plasma, no longer held together by gravitational forces, would begin expanding outward in all directions. But this wouldn't be a slow, gentle expansion. It would be explosive. Think of it this way. Imagine a balloon that's been compressed to a tiny fraction of its normal size. The moment you release the pressure holding it compressed, it doesn't gradually return to its normal size. It snaps back rapidly, often shooting away across the room. The sun's plasma, compressed by billions of years of gravitational pressure, would do something similar, but on an unimaginably larger scale. As the sun's material expanded outward, the density and temperature in its core would drop rapidly. Nuclear fusion requires very specific conditions to occur. The nuclei need to be close enough together and moving fast enough, which means hot enough, to overcome their electrical repulsion and fuse together. When the sun's core density drops below a critical threshold, fusion would simply stop. This wouldn't take very long. Within minutes of gravity's disappearance, the sun's core would expand and cool enough that nuclear fusion would become impossible. The nuclear furnace that has burned for 4.6 billion years would go cold, not because it ran out of fuel, but because it could no longer maintain the conditions necessary for burning. The same thing would happen to every star in the universe. The details would vary depending on the star's size and type. Massive stars, which burn much hotter and brighter than the sun, would face even more dramatic expansions as their enormous gravitational compression was suddenly released. These stellar giants might explode outward with such violence that they would briefly outshine entire galaxies as their compressed material rushed into space. Red giant stars, which are already in a somewhat expanded state as they near the end of their lives, might simply puff away like cosmic soap bubbles, dispersing their outer layers gently into space while their cores cooled and expanded. White dwarf stars present a particularly interesting case. These are the compressed remnants of sun-like stars that have already exhausted their nuclear fuel. A white dwarf is incredibly dense, about as massive as the sun, but only about the size of Earth. This density is maintained entirely by gravitational compression. Without gravity, a white dwarf would expand explosively, its compressed material rushing outward like the ultimate firework. The material that had been crushed into a space the size of a planet would suddenly be free to expand to fill a volume larger than the original star's main sequence size. Neutron stars, even denser than white dwarfs, would undergo even more spectacular transformations. These objects, which are the collapsed cores of massive stars, pack about 1.4 times the mass of the sun into a sphere only about 12 miles across. The matter in a neutron star is so compressed that a teaspoon of it would weigh about 6 billion tons on Earth. This matter is held in its ultra-compressed state entirely by Gravitational forces so strong that they overcome even the quantum mechanical forces that normally prevent particles from occupying the same space. Without gravity, neutron star matter would expand with indescribable violence, releasing enormous amounts of energy as the compressed particles finally had room to spread out. The most extreme case would be black holes, which we touched on earlier. Black holes represent the ultimate victory of gravity over all other forces. Regions where gravity is so strong that it has compressed matter beyond what we call the event horizon, creating regions from which not even light can escape. But what? Is a black hole in a universe without gravity? The mass is still there, but without gravitational forces to hold it in its ultra-compressed state. That mass would be free to expand. The result would be explosions that would dwarf anything else in the universe. As matter that had been compressed beyond the event horizon suddenly found itself free to expand and release all the energy that had been trapped within the black holes, gravitational prison, stellar nurseries. Those regions of space where new stars are currently forming would also lose their ability to function. Stars are born when gravity causes clouds of gas and dust to collapse and compress until they become hot and dense enough for nuclear fusion to begin. Without gravity, there would be no mechanism for this compression. The gas and dust in stellar nurseries would simply remain as dispersed clouds, never able to condense into new stars. This means that the universe would not only lose its existing stars, but would also lose its ability to create new ones. The era of star formation, which has been ongoing since shortly after the Big Bang, would end immediately and permanently. Binary star systems, where two stars orbit around their common center of mass, would see their components fly apart as the gravitational forces that kept them in orbit disappeared. Some of these systems are so close that material flows from one star to the other, creating spectacular phenomena like nova explosions. All of this stellar interaction would cease as the stars in binary systems went their separate ways. Variable stars, which change in brightness due to gravitational pulsations or interactions with companion stars, would stop their variability. As the gravitational mechanisms driving their changes disappeared, the universe would lose much of its dynamic stellar behavior, becoming a place where stars, if they still existed, would shine with constant brightness until their dispersing material became to spread out to emit significant light. The cosmic, distant scale, which astronomers use to measure distances to faraway galaxies, relies heavily on certain types of variable stars. Without these stellar lighthouses, our ability to map the universe and understand its structure would be severely limited, though this would be academic since the universe's large scale. Structure would be collapsing anyway. Perhaps most poignantly, the loss of stellar nuclear fusion would mark the beginning of the end for complexity in the universe. Stars are the cosmic factories that create elements heavier than hydrogen and helium. The carbon in our bodies, the oxygen we breathe, the iron in our blood, all of these elements were forged in the nuclear furnaces of stars and dispersed into space. When those stars died, without stars to create new elements, the universe would be stuck with only the lightest elements created in the Big Bang: hydrogen, helium, and trace amounts of lithium. The chemical complexity that makes planets' life, consciousness possible, would become impossible to create, making our gravity-free universe not just structurally empty, but also chemically impoverished. In this starless cosmos, the only sources of energy would be the residual heat from objects as they slowly radiated away their thermal energy into the cold vacuum of space. The universe would gradually cool toward absolute zero, becoming not just dark, but utterly cold and lifeless. As we reach the final stage of our thought experiment, we must consider the ultimate consequence of removing gravity from the universe. The complete unraveling of cosmic structure at every scale, from the smallest gravitational systems to the largest features of the cosmic web. We've seen how individual objects, planets, stars, galaxies would disperse when gravity disappears, but the loss of gravity would also mean the end of the universe's ability to organize itself into complex structures, marking not just the dispersal of existing cosmic architecture, but the permanent end of cosmic evolution itself. Let's start with the concept of cosmic time and evolution. The history of the universe has been a story of increasing complexity, driven largely by gravitational collapse. In the beginning, shortly after the Big Bang, the universe was remarkably smooth and uniform, just a hot, dense soup of particles and radiation with only tiny variations in density. Over billions of years, gravity amplified these tiny variations. Regions that were slightly denser than average attracted more matter, becoming even denser, which allowed them to attract still more matter. This process, called gravitational collapse, is responsible for every structure we see in the universe today, from the largest galaxy clusters down to individual planets. Without gravity, this process would not only stop it, would become impossible. The universe would lose its ability to build complexity, to create order from chaos, to evolve from simple to sophisticated structures. Cosmic evolution would end permanently. The cosmic web, that magnificent large-scale structure of the universe, consisting of galaxy clusters connected by filaments of dark matter and gas, with vast voids in between, would dissolve completely. This web represents the largest scale organization in the universe, structures so vast that they span hundreds of millions of light years. These cosmic structures exist because dark matter, under the influence of gravity, clumped together over billions of years, creating an invisible scaffolding upon which ordinary matter could accumulate to form galaxies and galaxy clusters. Without gravity, dark matter would simply spread out uniformly through space. The cosmic web would flatten into a smooth, structureless distribution of matter. The concept of cosmic horizons would also change dramatically. Right now, we live within several different types of cosmic horizons, boundaries beyond which we cannot see or be influenced by distant events. The particle horizon marks the edge of the observable universe, farthest distance from which light has had time to reach us since the Big Bang. But these horizons exist partly because of gravitational effects on light, space-time. In Einstein's theory of general relativity, gravity isn't just a force, it's the curvature of space-time itself. Massive objects curve space-time, and this curvature affects how light travels through the universe. In a universe without gravity, space-time would be perfectly flat, like a stretched sheet, with no bowling balls to create dips and curves. Light would travel in perfectly straight lines, and the complex gravitational effects that influence our observations of distant objects would disappear. While this might seem like it would make astronomy simpler, it would actually make it much less interesting, since many of the most fascinating phenomena in the universe, black holes, gravitational lensing, time dilation are gravitational effects. The expansion of the universe itself might be affected. Right now, the universe is expanding, and this expansion is accelerating due to dark energy. But the rate of expansion and the universe's overall dynamics are influenced by the TEHS, gravitational effects of all the matter and energy it contains. In a universe without gravity, the relationship between matter, energy, and cosmic expansion would be fundamentally different. Dark energy might still cause expansion, but without gravity to provide resistance to that expansion, the cosmos might expand much more rapidly, further accelerating the dispersal of matter and energy. The thermodynamic fate of the universe would also change. In our current universe, gravity plays a crucial role in the long-term evolution of cosmic structures. Even as the universe expands and cools, gravity can still bring matter together to form new structures, create new stars, and maintain complexity for trillions of years into the future. But in a gravity-free universe, there would be no mechanism to counteract the universal tendency toward increasing entropy. Matter and energy would spread out uniformly through space. Temperatures would equalize everywhere. The universe would reach a state of maximum entropy much more quickly than it would. Otherwise, this would represent the ultimate heat death of the universe's state, where no more work can be done, no more complexity can arise, and no more interesting events can occur. Instead of taking perhaps 10,100 years to reach this state, as some models of our current universe suggest, a gravity-free universe might reach maximum entropy in a relatively short cosmic time. The very concept of place would lose meaning in such a universe. Right now, we can describe locations in the universe relative to gravitational structures, near stars, within galaxies, around galaxy clusters. These structures provide reference points, cosmic addresses that allow us to navigate the universe. Conceptually, without gravitational structures, the universe would become a vast, undifferentiated expanse with no meaningful landmarks. Every location would be equivalent to every other location, with no way to distinguish one region of space from another, except by arbitrary coordinate systems. Even more fundamentally, the universe would lose its ability to support complexity of any kind. Life, as we know it, depends on complex chemical processes that require energy sources, stable environments, and the ability to concentrate and organize matter. All of these requirements depend directly or indirectly on gravitational effects. Planets provide stable platforms for life because gravity holds them together and keeps them in stable orbits around energy-providing stars. Stars provide energy because gravity compresses their cores enough to sustain nuclear fusion. Complex chemistry is possible because gravity helped form the heavy elements in stellar cores and disperse them through supernovae. In a gravity-free universe, none of these prerequisites for complexity would exist. There would be no stable platforms, no long-term energy sources, no way to concentrate matter into the complex arrangements that life requires. The universe would be not just lifeless, but incapable of supporting life. Perhaps most profoundly, such a universe would be incapable of containing observers. There would be no planets for life to evolve on, no stars to provide energy, no complex chemistry to build living systems. The very questions we're asking in this thought experiment, what would happen? What would it look like? Would become meaningless because there would be no minds to ask them and no experiences to observe the answers. In the end, a universe without gravity would be not just different from our own, but almost incomprehensibly impoverished. It would be a cosmos without structure, without complexity, without the beautiful hierarchy of organizations that makes our universe so rich and fascinating. It would be a place where entropy reigns supreme from the beginning, where nothing interesting ever happens, and where the very concept of interesting would have no meaning. It would be the most fundamental sense. A universe that never learned to dance. As we slowly drift back from our impossible journey through a gravity-free universe, it's worth pausing to consider what this thought experiment reveals about the nature of reality itself. We've witnessed the complete unraveling of everything we consider normal, stable, and permanent. We've watched planets disperse, stars extinguish, galaxies scatter, and the very fabric of cosmic structure dissolve into chaos. But in observing this cosmic catastrophe, we've also discovered something profound about the universe we actually inhabit, how extraordinarily, beautifully, improbably organized it is. Think about it for a moment. In our thought experiment, removing just one of the fundamental forces of nature, gravity, was enough to completely destroy not just life, not just planets, not just solar systems, but every structure in the universe at every scale. From the smallest asteroid held together by its own weak gravitational pull to the largest galaxy clusters spanning hundreds of millions of light years. Everything depends on this single, invisible, seemingly simple force. This reveals something remarkable about the delicate balance that makes our universe possible. We live in a cosmos where the fundamental forces are perfectly calibrated to allow complexity to arise and persist. If gravity were much stronger, stars would burn out quickly, and galaxies would collapse into black holes. If it were much weaker, stars couldn't form at all, and matter would never clump together into planets, galaxies, or any organized structures. But it's not just gravity. The strength of the electromagnetic force, the rate of cosmic expansion, the mass of fundamental particles, the properties of space and time itself, all of these parameters seem to be set at precisely the values needed to allow for the existence of stars, planets, chemistry, and ultimately, life and consciousness. Physicists call this the fine-tuning problem, and it's one of the deepest mysteries in cosmology. Why do the laws of physics seem so perfectly arranged to allow for complexity in life? Is it pure coincidence? Are there vast numbers of universes with different physical laws? And we happen to live in one of the rare ones where conscious observers can exist. Or is there some deeper principle that necessitates these particular values? Our thought experiment doesn't answer these questions, but it does make them more vivid. By imagining what the universe would be like without gravity, we gain a deeper appreciation for how special our actual universe is. We see that the existence of every structure we take for granted, from mountains to galaxies, represents a victory of organizing forces over the natural tendency toward chaos and dispersal. There's also something humbling about realizing how completely we depend on forces we can't see, control, or fully understand. Gravity is invisible, silent, and so constant that we usually ignore it entirely. Yet our entire existence and the existence of everything we care about depends absolutely on its continued operation. This dependence extends far beyond the obvious fact that we'd float away without. Gravity, our planet's spherical shape, its atmosphere, its oceans, all products of gravitational forces, the sun's ability to shine, providing the energy that powers virtually all life on Earth, dependent on gravitational compression. The moon's stabilizing influence on Earth's rotation and tides, gravitational phenomenon, even the formation of the heavy elements that make up our bodies happened inside stars whose existence depended on gravitational collapse. In a very real sense, we are gravity's children, beings who exist only because this fundamental force has spent billions of years patiently organizing the cosmos into the complex structures that make life possible. Our bodies are made of stardust, held together by electromagnetic forces. But that stardust was created in stellar furnaces powered by gravity. We live on a planet whose very existence is a gravitational phenomenon. This perspective can change how we see our place in the cosmos, rather than being insignificant specks in a vast, indifferent universe. We can see ourselves as the universe becoming conscious of itself. We are complex arrangements of matter and energy that the cosmos has managed to organize into thinking, feeling, wondering beings. We are not separate from the universe. We are the universe. It's temporarily arranged into a form capable of contemplating its own existence. Our thought experiment also reveals the deep interconnectedness of everything. We couldn't remove gravity from just Earth, or just the solar system, or just our galaxy. Gravity is a universal force, and removing it anywhere means removing it everywhere. The fate of every object in the universe is connected to every other object through gravitational relationships that span the cosmic web. This interconnectedness extends beyond gravity to all the fundamental forces and properties of nature. Electromagnetic force that holds atoms together is related to the weak nuclear force that powers certain types of radioactive decay. Einstein's equivalence of mass and energy change any one of these forces, and you change everything. There's something both terrifying and comforting about this universal interdependence. Terrifying because it reveals how fragile our existence is, how dependent we are on the continued operation of forces beyond our control. But comforting because it shows that we are not isolated, not separate, not alone. We are a part of a vast, interconnected, cosmic dance that has been going on for nearly 14 billion years. Our thought experiment also highlights the role of emergence in the universe. Emergence is the phenomenon where complex behaviors and properties arise from the interaction of simpler components. Individual atoms don't have consciousness, but arrange enough of them in the right way, and consciousness emerges. Individual stars don't have the ability to create life, but arrange them into galaxies with planets orbiting in the right zones, and life can emerge. Gravity is one of the key forces that enables emergence in the universe. By bringing matter together and holding it in stable configurations, gravity creates the conditions where higher-order phenomena can arise. Without gravity, there would be no platforms for complexity, no way for simple components to arrange themselves into more sophisticated systems. This makes our own existence seem even more remarkable. We are not just the products of biological evolution, but of cosmic evolution. billions of years of gravitational collapse, stellar nucleosynthesis, planetary formation, and chemical evolution that created the conditions where life could begin and develop into conscious beings capable of pondering their own origins. Perhaps most importantly, our thought experiment reminds us not to take the universe for granted. The fact that we live in a cosmos where gravity works, where stars shine, where planets exist, where chemistry is complex enough to support life's none of this, was inevitable. It represents an almost miraculous balance of forces and properties that could easily have been otherwise. Every time you feel the familiar tug of gravity keeping your feet on the ground, remember that you're experiencing one of the fundamental forces that makes existence possible. Every time you see the moon in the sky, remember that you're looking at a gravitational dance that has been going on for billions of years. Every time you feel the warmth of the sun on your face, remember that you're receiving energy from a gravitational collapse that began before the Earth was formed. We live in a universe that learned to dance, and we are part of that dance. What an extraordinary thing that is. As we near the end of our cosmic journey, let's take a moment to appreciate gravity, not as the destroyer we imagined it could be by its absence, but as the gentle architect it actually is in our universe. Throughout our thought experiment, we've seen what happens when this force disappears. But perhaps we haven't fully appreciated what happens when it's present, the quiet miracles it performs every moment of every day. Gravity is, in many ways, the most democratic of the fundamental forces. It doesn't care about electric charge like the electromagnetic force does. It doesn't operate only at tiny distances, like the strong and weak nuclear forces. Gravity responds only to mass and energy, and since everything in the universe has mass and energy, everything in the universe experiences gravity. This universality gives gravity a kind of cosmic compassion. It embraces everything equally: stars and planets, galaxies and grains of sand, you and me. It doesn't discriminate, doesn't play favorites, doesn't judge. It simply responds to the presence of mass and energy by creating the gentle curves in space-time that we experience as gravitational attraction. And what beautiful curves they are! The elliptical orbits of planets around stars, the graceful spiral arms of galaxies, the complex dance of binary stars around their common center of mass. All of these are gravity's artwork, painted in motion across the canvas of space and time. Consider the elegance of planetary motion. For millennia, humans struggled to understand why planets move the way they do. Ancient astronomers created elaborate systems of circles within circles, trying to explain the complex apparent motions of planets against the background stars. It wasn't until Newton that we realized the simple truth. Planets follow elliptical orbits because they're falling toward their stars, but moving sideways fast enough that they never actually reach them. Every planet in our solar system is perpetually falling toward the sun, and yet never getting closer to it on average. It's a cosmic magic trick that has been going on for billions of years. It's performed by nothing more than the curvature of space-time around a massive object. The same gravitational embrace that keeps planets in orbit also gives them their spherical shapes. There's something deeply satisfying about the fact that gravity naturally creates spheres the most perfect, symmetrical shape possible. Every planet, every star, every sufficiently large moon is a sphere because gravity pulls equally in all directions, creating objects with no preferred orientation, no natural top or bottom. Gravity is also an artist of time. Einstein showed us that gravity doesn't just curve space, it curves time as well. Time passes more slowly in strong gravitational fields than in weak ones. This means that time itself flows differently on the surface of the Earth than it does in orbit around our planet. GPS satellites must account for this time dilation to maintain their accuracy. This temporal artistry creates one of the most beautiful phenomena in astronomy: gravitational time dilation. Near black holes? As you approach the event horizon of a black hole, time slows down relative to distant observers. From the perspective of someone watching from far away, you would appear to slow down and freeze at the event horizon, your image redshifted to invisible wavelengths as the universe ages around you. It's a kind of immortality, though not the kind anyone would choose. Gravity also performs more subtle artworks that we often don't notice. The tides that rise and fall in Earth's oceans are gravity's gentle massage of our planet. The moon's gravitational influence creating a rhythm that has shaped life for billions of years. Many organisms time their reproductive cycles to tidal patterns. It's possible that the tidal pools created by gravitational tides experiences these gravitational tides. The planet's surface rises and falls by several inches twice a day as the moon's gravity tugs on it. We don't notice this solid Earth tide because we rise and fall with it, but sensitive instruments can measure it easily. It's a reminder that even seemingly solid objects are actually fluid on cosmic timescales. It's constantly reshaped by gravitational forces. Gravity is also responsible for one of the most generous phenomena in the universe, the existence of stars. Stars are essentially gravity's gift to the cosmos self-sustaining. Fusion reactors that convert the universe's most abundant element, hydrogen, into both heavier elements and enormous amounts of energy. The process is beautiful in its simplicity. Gravity pulls hydrogen gas together until it becomes so compressed and hot that the hydrogen nuclei overcome their natural repulsion and fuse into helium, releasing energy in the process. This energy pushes outward, creating a perfect balance with the inward pull of gravity. The result is a stable, long-lasting source of energy that can shine for billions of years. And when stars die, gravity performs its final act of generosity. In some cases, gravity causes dying stars to explode as supernova, scattering the heavy elements they've created throughout their lives into space, where they can be incorporated into new stars, planets, and eventually living beings. In other cases, gravity compresses the star's core into exotic objects like neutron stars or black holes, creating some of the most extreme and fascinating phenomena in the universe. Gravity even has a sense of humor. It creates gravitational lenses, where the space-time curvature around massive objects acts like a cosmic magnifying glass, bending and focusing light from more distant objects. These gravitational lenses allow us to see galaxies that would otherwise be too faint and distant to observe. Gravity essentially holds up a telescope for us. It's helping us explore the deepest reaches of space and time. There's also something poetic about gravity's weaknesses. Of all the fundamental forces, gravity is by far the weakest. The electromagnetic force that holds atoms together is about 1,036 times stronger than gravity. You can demonstrate gravity's weakness easily when you pick up a paperclip with a magnet. The electromagnetic force from that tiny magnet overcomes the gravitational pull of the entire Earth, and yet, despite its weakness, gravity dominates the large-scale structure of the universe. This is because gravity is always attractive, unlike electromagnetic forces, which can repel as well as attract, and it has infinite range. Given enough mass and enough time, gravity always wins. It's the cosmic equivalent of the tortoise and the race with the hares low and steady, but ultimately triumphant. This weakness might actually be essential for the universe's beauty. If gravity were much stronger, structures would collapse too quickly for complexity to develop. Stars would burn out rapidly, black holes would dominate, and the universe would be a much more violent, chaotic place. Gravity's gentleness allows for the slow, patient construction of cosmic architecture. Perhaps most remarkably, gravity seems to have a creative intelligence. From the seemingly random distribution of matter shortly after the Big Bang, gravity has constructed a cosmos of extraordinary beauty and complexity. Galaxy clusters arranged in vast webs, spiral galaxies with elegant arms, planetary systems with intricate orbital resonances. All of this emerged from gravity acting on small, random variations in the early universe. It's as if gravity is a cosmic composer, taking the simple notes of mass and energy and orchestrating them into the symphony of the universe. Every structure we see, from the smallest asteroid to the largest galaxy cluster, is part of gravity's composition, playing its part in the ongoing cosmic music. And we are part of that music too. The calcium in our bones was forged in stellar cores held together by gravity. The iron in our blood was scattered by supernova explosions driven by gravitational collapse. The water we drink follows gravitational gradients to form rivers, lakes, and oceans. Even the neural impulses in our brains, which allow us to think about gravity, depend on the complex chemistry that was made possible by billions of years of gravitational construction. In contemplating gravity's beauty, we're not just appreciating an abstract force, we're appreciating the architect of everything we know and love. Gravity built the stage on which the drama of existence plays out, and it continues to maintain that stage with patient, invisible artistry. There's something deeply moving about the realization that this force, which we barely notice in our daily lives, is actually the silent partner in every moment of our existence. Every breath we take, every step we make, every thought we think is possible only because gravity has spent billions of years preparing the universe for this moment. Gravity asks nothing of us in return. It doesn't require our understanding, our gratitude, or our acknowledgement. It simply continues its work, day and night, second by second, holding together the cosmic structures that make our lives possible. It is perhaps the closest thing to unconditional love that exists in the physical universe of force that embraces everything equally and asks nothing in return. And so we come to the end of our impossible journey, floating gently back to reality from a universe where gravity ceased to exist. We've witnessed the dissolution of everything, planets dispersing into clouds of debris, oceans forming floating spheres, buildings drifting apart like dream fragments, the sun expanding into a cooling cloud of plasma, galaxies scattering there. Stars across the void like cosmic dandelion seeds. It has been, perhaps, the ultimate bedtime story, a tale of universal dissolution told softly enough that it might carry you into sleep, but profound enough to linger in your dreams. We've explored what might be the most catastrophic change imaginable to our universe, and yet we've done it safely. From the comfort of a cosmos where gravity still works perfectly, where stars still shine, where planets still orbit in there, ancient patterns. What strikes me most about our thought experiment is not the destruction we imagined, but the incredible improbability of what we normally take for granted. Every structure in our universe, from the smallest pebble to the largest galaxy cluster, exists in defiance of chaos. The natural tendency of the universe is toward maximum entropy, toward dispersal and dissolution, toward the even distribution of matter and energy through space. Yet here we are, a cosmos filled with stars and planets, with intricate chemical processes, with life and consciousness and poetry. We exist because gravity, working patiently over billions of years, has managed to create islands of order in an ocean of entropy. Every atom in your body is part of a temporary but beautiful arrangement that stands against the universal tide of disorder. There's something almost miraculous about this when you really contemplate it. The universe could so easily have been empty, structureless, lifeless. And perhaps in most possible versions of reality, it is. But in this particular cosmos, in this specific arrangement of physical laws and constants, gravity has learned to dance, and in dancing, it has created the conditions for matter to become conscious of itself. You are the universe's way of knowing that it exists. It's the thoughts you're thinking right now, the sense of wonder you might feel contemplating the cosmos, the very capacity for curiosity that brought you to listen to this exploration. These are not separate from the physical universe, but expressions of it. The same gravitational processes that formed galaxies and stars also, over deep time, created the conditions for your existence. In our imagined gravity-free universe, there would be no observers, no consciousness, no one to ask what if, or to imagine alternatives. The very questions we've been exploring together would be impossible in such a cosmos, because there would be no minds to formulate them, and no stable structures to provide the platforms where minds could evolve. This makes our existence seem both more precious and more connected to the cosmic whole. We are not accidental byproducts of an indifferent universe. We are the universe's way of wondering about itself, of imagining alternatives, of appreciating the delicate balance that makes complexity possible. And what a balance it is. If the fundamental forces were slightly different, if the expansion rate of the universe were a bit faster or slower, If the properties of matter and energy were altered in seemingly minor ways, none of this would exist. No stars, no planets, no chemistry complex enough for life. No evolution, no consciousness, no capacity for wonder. Yet here we are, in probably conscious matter, pondering its own existence, spinning on a spherical planet held together by gravity, orbiting a star powered by gravitational compression in a galaxy of hundreds of billions of other stars, in a universe that has been expanding and evolving for nearly 14 billion years. The odds against our existence seem astronomical, and yet here we are, proof that the impossible is possible. Our thought experiment has also reminded us of the profound interconnectedness of everything. We couldn't remove gravity from just one place or one object, a universal force that connects every particle of matter in the cosmos to every other particle. The gravitational field you're creating right now, simply by having mass, extends infinitely through space, subtly influencing the motion of distant galaxies, and the gravitational fields of those distant galaxies, in turn, influence you, this web of gravitational relationships. It means that you are not separate from the cosmos. You are woven into its very fabric. Every star in the sky is connected to you through gravity's infinite reach. Every planet, every asteroid, every grain of cosmic dust participates in the same universal dance of mass and space-time curvature. In a very real sense, the universe is not something external that you observe. It's something you participate in, something you are part of, something that exists as much within you as around you. The iron in your blood was forged in stellar cores. The calcium in your bones was created in supernova explosions. The water in your cells has been cycling through the cosmos for billions of years, and someday, the atoms that currently compose your body will return to the cosmic dance, perhaps becoming part of new stars, new planets, maybe even new forms of life and consciousness. You are a temporary arrangement of cosmic matter that has learned to think and feel and wonder. And when that arrangement disperses, the matter will continue its journey through space and time, carrying forward the possibility of new arrangements, new forms of beauty and complexity. There's something comforting about this cosmic perspective. Our individual lives are brief, but we are part of something much larger and longer lasting. The universe that created us will continue creating new forms of beauty and complexity long after we're gone. The same gravitational forces that shaped our existence will go on shaping the existence of future worlds, future life, future consciousness. In imagining a universe without gravity, we've gained a deeper appreciation for the universe. We actually inhabit a cosmos where invisible forces create visible beauty, where matter organizes itself into ever more complex and wonderful forms, where the dance of mass and energy has created the stage on which the drama of existence unfolds. So tonight, as you drift towards sleep, remember that you are held in gravity's gentle embrace. The earth beneath you is holding you close. The moon is pulling softly on the water in your body. The sun is maintaining its perfect fusion fire 93 million miles away. And all the stars in the sky are participating in the same cosmic choreography that has been going on for billions of years and will continue for billions more. You are part of something magnificent, a universe that learned to create beauty, complexity, and consciousness through the patient artistry of fundamental forces. Rest well in that knowledge, carried gently into dreams by the same gravitational currents that carry planets around stars and stars around galaxies. And if you found some peace or wonder in our impossible journey tonight, please consider sharing it with others who might need a gentle reminder of how extraordinary our ordinary universe really is. Subscribe to Sleep Scientist for more explorations of the cosmos that surrounds and sustains us all. Leave a comment telling us where in the world you're listening from. It's always wonderful to see how far our little community of cosmic contemplators reaches across this gravity-bound planet we call home. Until next time, sleep peacefully under the stars, held safely in the arms of gravity, dreaming of impossible worlds while appreciating the miracle of the possible one you inhabit. Sweet dreams, fellow travelers. The universe is vast, but you are part of it, and it is part of you. And that connection will continue long after your dreams fade into morning light.